So looking at the second problem of the human eye lens due to the change in the refracting index, we have the condition called hypermetropia, also called far-sightedness. So here the key point, the far-sightedness itself indicates what's the problem. The person will not be able to see nearby objects. So distant objects can't be seen, and which obviously means that nearby objects cannot be seen. Nearby objects are not visible. Now we know that there is a near point for the human eye which is approximately 25 centimeters. This basically means that for hypermetropic eye, the near point, or the point at which you can clearly see a near object is further from 25 centimeters, which means that you can't. So if you are trying to read a book at around 25 centimeters in front of the eye, you won't be able to read it. So it simply means that the near sight, or the near clear sight of the human eye in this particular case is something like 25 plus. I mean, it's more than 25 centimeters. So so you have the lens. So this is a retina, and so the new near sight area, I mean the new location is, we can call it N. So this is the new site is at N, and this is the, suppose this is the this is what it should have been, that is N dash. So what is happening here is that for an object which is a little farther away from 25 centimeters, obviously you are getting a the focus is being formed on the retina. You are able to see the image, but for this the actual near sight location, that is at 25 centimeters, what is happening is that so for the rays which are emanating from that location, so for that object, that's for the rays which are coming from the normal near sight location, that is at 25 centimeters from the lens. Interestingly, the image is getting formed behind the retina, so it is behind the retina. Now how can we rectify this particular condition? That's what we are looking at. So let's look at the how we can rectify this particular condition. So this should have been the normal distance of near vision. So this is a new near vision, and obviously it is from here, the rays emanating from here, the focus is getting the focus is behind the retina. So if you keep a convex lens over here, what happens is that you can see that problem can be rectified. That is, the image will be forming on the retina. So you are using a convex lens, and you can see that image is getting formed on the retina. And obviously the case of the object which is beyond that 25 centimeters, which we have already denoted as N, that obviously it's clearly visible. It's also obviously clearly visible. So you can see that by using a convex lens of appropriate. So by using a convex lens of appropriate power, you can rectify the condition due to hypermetropia. To conclude this particular section, so what is the biological reasons behind such a situation? Obviously, one reason could be that the focal length of the eye lens is too long, or now suppose this is the eyeball and this is the focus, this is the lens, and we are having the focus here, the normal focus. So suppose what happens if the eyeball is a little something like it becomes reduced. So, I mean the size of the eyeball gets reduced. You can see that the focus will be behind retina. So that's the second condition. So the eyeball becomes too small. So these are the two usual situations, two usual conditions, two usual reasons for the eye condition called hypermetropia. Thanks.